So, warm welcome to everyone. I'm Viktor Somogyi, and today I will tell you about the story that how we can transform real data echoes of Venus into scientific map layers that anyone can use and reproduce with a completely open source toolkit. First of all, I'm an external researcher of the European Space Agency. I'm Hungarian, so I traveled here from Hungary, very far away. I have a company back home which is called Netwerk Media. This project is financed and run by the European Space Agency. You can ask a question that why Venus is so special, and the short answer is, but we are going to have a longer answer for that as well, because its surface is optically blind. So if we try to take pictures, welcome, hello. So if we try to take pictures, we only see a dense and sulfuric cloud layer. I'm going to show you an example of that a little later. It is very interesting. So if we try to take pictures, basically we can't see nothing. Radar, however, is different. It sends down radio waves and forms the patterns of echoes, so we can reconstruct what lies beneath. So basically, it's like if you try to imagine the work of a radar, it's like when you clap your hands in a dark room, and from the echo, you can sense the size and the shape of the room. But of course, the Magellan probe did the same thing, only with radio pulses and an antenna. And our goal in this project is basically to take a raw speckled radar mosaic and build a Google Maps-like experience where you can switch on different layers. So you can say that here is, for example, a crater rim, or here is a volcanic dome, here runs a ridge, and so on. And from these layers, researchers can immediately can take measurements, make statistics, and buy hypotheses. And all of this, because we are on the open source summit. So basically, I'm the machine learning leader in this project, the machine learning dev lead. But today, I more or less would like to emphasize the open source regards of this project. So all of this is built in an open source environment, Linux, plus Python, PyTorch, scikit-learn, GeoPandas, QGIS for labeling, and of course, at least for me, this is a natural thing, AWS SageMaker for training. And the most important principle of this project is there is no magic box. Every step is transparent, documented, and reproducible. And not just for us, but for anyone who wants to rerun this process. And I'm going to talk a little more about that later. But here comes our next slide, which is the project overview. I always say that this project is both kind of a space exploration story and a software engineering story. The workflow looks like this. Basically, raw data comes in. These are the radar mosaics. It is systematically transformed, which is called the preprocessing, and the model learns. This is the GPU training, and then we measure like accuracy, error rates, and curves, and so on. And then we output. The output, in our case, is a GeoJSON or GeoTIFF file or layers. And from a developer point of view, it's more or less an ETL plus MLOps pipeline. ETL is because we are extracting, transforming, and loading the data, and MLOps because machine learning operations, training, evaluation, and release, and all handled with an engineering discipline. And to imagine it's like a well-built backend, that every version is, every step is versioned, logged, and reproducible. And we also have a kind of a CI/CD feeling as well, because if anybody has a better idea, you are free to submit a pull request. If something breaks, then we can roll back to a previous stage, and the whole environment is basically containerized in Docker. So the infamous, it's work on my machine, but not on yours. I think that everyone had some kind of problem in their life already at some point, hopefully back in the future, back in the past. So that disappears as the environment is identical everywhere. And importantly, it is very important that I always say this, that open source in our case is not just that free software, it's basically a cultural choice, because we try to provide runnable code and data lineage behind our scientific claims. This is very important, and that means that you can always trace back which output came from which input through which steps and parameters. This makes the project and science not only impressive, at least in my opinion, but also verifiable and reproducible. So in short, this project, in my opinion, is a good intersection of software engineering and good science, and we are not building only a one-off demo, but a system that you can run, criticize, and extend yourself. But here comes the next question. Why is Venus? It's because Venus is a really, really interesting planet. Venus is Earth's twin in size and mass, but in almost every other aspect, it's completely the opposite. It has a very, very dense atmosphere. I'm going to show you some photos of how Venus looks like in real life. It has a dense atmosphere. It's mostly carbon dioxide and exerting a pressure of 92 times greater than the Earth's at sea level. And that's like, imagine standing a kilometer underwater, except instead of water, you are on Venus in a very hot and toxic gas clouds. So add this to the sulfuric acid clouds, which blocks everything in the optical range. And here comes the radar part, because we can't see anything in the optical range. And if that weren't enough, the average temperature is about 460 degrees Celsius, which is actually hot enough to melt lead right on the surface of Venus. So Venus is very, very unusual, and not even in the already described regards, but even if its motion, it rotates very, very slowly and in retrograde. Retrograde means that the direction of the circling is opposite to Earth. In fact, one day in Venus is longer than 1 year in Venus. It's a slowly moving planet. That alone shows how this word alien to us. And under such conditions, of course, optical cameras are blind, because we can't see any surface at all. Radar, however, sees through the clouds and maps the planet's skin-like surface. And, but why do we care about the surface? Because surface features tell the story of the planet inner's life. The number of distribution of the craters, for example, reveal the surface age. We have a general rule in planetography that the more the craters, the older the surface. As fewer craters means something has, for example, refreshed the landscape, like lava or tectonics or atmospheric erosion. And our goal is to identify this basically automatically and consistently across large regions, and then we can build more accurate and unified pictures of the Venus past and present. My next slide is about the Magellan, because we already got to know our target planet, Venus, but now let's get to know the spacecraft that underpins our entire story, which is the NASA's Magellan probe. Magellan arrived to Venus at 1990, and instead of using optical cameras, it mapped the surface with a synthetic aperture radar, which is short for SAR or SAR. This was revolutionary because radar could penetrate the thick clouds and map almost the entire planet. The trick behind SAR is very, very simple, but it's very powerful. It makes many, many small movements while the spacecraft moves, then combines them cleverly as it is observed the planet with a gigantic antenna. This makes side-looking resolution very sharp, and I'm going to show you some examples of the actual image that Magellan probe took about Venus a little later, but it is very important to understand first. That the radar image is basically, it's not a photograph. We don't see colors, we see how strongly the radio waves were reflected from the surface. And this thing, I mean, how strongly the radio reflected to the surface depends on three things. First, the micro and macro roughness of the terrain. The second thing is whether the slope is tilted towards us or away from us. Tilted towards us is that the slope looks to the direction of the satellite or looks away from the satellite. And the electromagnetic properties of the rock, basically it means that how much conducts or absorbs the signal. And to lay it in a real-life example, it's basically you should think it like, I don't know, shining a flashlight in a room. But instead of watching the light, you hear the light with a microphone. And with that microphone, you would hear the surface of the wall where you are heading your flashlight. So this is how basically a radio telescope or a radio photographer satellite works. And the results were long and striped images because the spacecraft always looks sideways and swept across the planet in strips. Okay. And what is another important thing that from our perspective, this data is gigantic TIFF or GeoTIFF files, sometimes tens of gigabytes in size. I'm going to tell you a little more about the pre-processing of these huge images later, but because of course, as you can imagine, normal human being is unable to work with such large files. I had my headaches as well back in the time. But first, a few things about the operation of a synthetic aperture radar. So basically, this can be imagined like a very, very disciplined panoramic photo. As the spacecraft moves along its orbit, it sends short radar pulses, which we call pings, down to the surface. And from the echo, we can record not only when it comes back, that gives us the distance, but also the state of the wave's oscillation, which we call the phase. And the trick is that we add up and combine many of these tiny little measurements as we are observing the surface with a giant razor-sharp antenna. And this is where the name is also coming from. It's a synthetic aperture. And there are two kinds of resolution, but I'm trying to be not too technical with regards of the technicalities operation of the SAR, but it's very interesting that we have two kinds of resolution. First is the range resolution. It shows how well we can separate features at different distances from the sensor, and this is mostly determined by the signal's bandwidth. The second resolution we have is the azimuth resolution. I think you guys already heard that word azimuth. If you're a little involved with the skies or stars. So the sharpness of the features along the flight direction is the azimuth resolution. And here we have another kind of information, which I think you have already seen or heard, which is the Doppler effect. This is basically the frequency shift caused by the motion. And this also adds extra information to our radar picture. I don't know who has experienced the Doppler effect in real life. Yes, so basically, I think everybody experienced that effect. So basically, it is when, for example, an ambulance siren sounds high-pitched as it approaches, and then it sounds lower when it passes. This is the exact same phenomenon we are using, but not in sound, but in radar. So far, we've checked how the image is built, and next we are going to check what it looks like when we first glance at raw radar mosaic. So this is, you can see my cursor or not? No, okay. Anyway, so basically this is how a radar mosaic looks like. And when we first look at this radar mosaic, the first impression, it is very grainy. But this is not only grains, this is called speckle. And this is very important because it's not just a photographic noise, because a radar image is not a photograph. So it's not photographic noise that should be smoothed out. And this is just a natural consequence of a radar. Because what happens? Because like countless tiny reflections come back from the surface, each with a slightly different path length. And the waves then add up or cancel each other. It works the same when, for example, the waves on the water meeting, sometimes they form a high crest and sometimes they form a trough. So the radar doesn't ruin the image. In fact, the texture exists because of its sensitivity. Just a moment. I'm sorry? You could see it now? Okay. Anyway, I won't count on it too much. Here on this image you can see layover, shadow, and foreshortening. These are another striking phenomenons in the geometric distortion, because the radar, as I already told you, looks sideways. It's not it doesn't look directly to the surface of the planet. Foreshortening is basically if a slope tilts toward us, then echoes arrive closer together in time, so the slope looks compressed in the image. The layover is, for example, when a mountain's peak signal arrives earlier than the base, then the peak falls over in the slope of the image. And the shadow, as you can see, that layover looks like as it was a snowy mountain, but unfortunately, Venus doesn't have water currently. Actually, it had. They just figured it out. A group of Italian researchers found traces of water on Venus, I don't know, 1 year or something like that. They were using for their research the exact same photograph that we are using now, this Magellan probe image. And the third one is the shadow. So far side of the slope is invisible to a radar, then no signal returns, and the image shows like a black shadow, as you can see. But I already told you, but I'd like to emphasize it, that these are not errors, but these are natural consequences of the radar side-looking perspective. And the model must not just learn what a crater looks in the photo, but it must actually think like a radar. So understanding that bright and dark pixels are results of physical reflection and geometry, because we are sensing not light here in this radar image, but we are sensing physics. And now I would like to show you a very short visualization of Venus. Actually, I tried two kind of things. So first, I'm going to show you this one. So this is how Venus looks like when, we are using Space Engine, and this image is using the Magellan probe photo that was photographed in 1990. And you can notice wherever we look, we can only see a thick and whitish yellow cloud layer. So optically, we are completely blind. We could say nothing about what lies on the surface, and the image helps us to understand why we are forced to use a radar. And I also prepared a couple of more images because there is an option in this software where I can turn off the cloud layer on Venus, and then I turn off the atmosphere layer on the Venus. So if Venus would look like this in real life, we could use normal photographic satellites like we use on Earth. But unfortunately, it doesn't look like this. And this is Venus surface when the cloud layer is enabled. This is Venus surface when the cloud layer is disabled, but the atmospheric layer is enabled. And this is when both the cloud and the atmospheric layers are disabled in the surface of Venus. So here comes the key shift that the radar, as I told you, works day and night through clouds in any weather and doesn't care about color, only the echo matters. How strong it is and what angle it arrives and what kind of pattern it draws. So when I later show you bright and dark patches, grainy stripes on the slides, all of those are the fingertips of the surface. And this is not a noise, but the planet's physical response when we tap its surface with radio waves. And this is exactly what the model must learn. To reliably recognize these patterns, even if viewing angle changes or the single strength varies or the surface type differs. And yes, so now that we checked our target planet, now we are checking of how we are about to build up this project in open source platforms. Because our goal is twofold. First, we need to segmentate, and then we need to vectorize. The segmentation and vectorization. Segmentation, you can imagine, like a coloring book. By pixel, we can say what each pixel represents. And this pixel might belong to a crater or rim or volcanic dome or a tectonic ridge or any other kind of geographical pattern on the surface of Venus. And the vectorization, on the other hand, is like drawing the outline around this colored-in patch. And this way, from the raw, grainy radar image, we get the points, lines, and polygons. These can be measured, sorted, filtered, and used in statistics. And why it is very important? Because geologists who are going to be using our output data are thinking in layers. They don't really care about what the AI thinks about the image. They just want to use the layers. For example, from a crater layer, we can ask that what is the crater density in a given region. Or, for example, a ridge network, we can derive length distributions and orientations, which already tells us about the stress field acting in the crust. And the vector format comes as a GeoJSON. It is very easy to version, to diff, and to connect with other layers like topography, geography maps, or even later mission data. And if another GIS format is needed, in the couple of slides later, we are going to be talking about what is GIS actually and what's a QGIS software, which is also an open source software. But if another GIS format is needed, it can easily be exported to shapes file or geo package. And I always tell this when I talk about this project, that we have a mantra for this project is raw, mask, vector, and then science. Because from raw radar echo, we are getting the masks. From the masks, we are getting the vector, and from vector, we are getting to the science. And this is how an echo becomes not just a pretty overlay, but a measurable layer. And this is very important, that for the output, we need to measure everything. You can think of a radar image like, I don't know, a painting. It can be beautiful, but it's very subjective. But once it becomes vectors, it won't be only beautiful and subjective, but we can start to ask questions about it. And this is a very nice image. So basically, when we are talking about the planet's whole radio photograph, we are talking about this. This image is a very small version of the actual image, which is 60 GBs in size. If you want to try to experiment it, actually you can download it from the Magellan's probe websites from, I don't know which NASA site, but maybe I will take a look on it if you're interested. And now we get to the complete workflow overview. So basically, we have 5 main steps, and each step has its own quality gate. The first one is annotation in QGIS. I already told you about QGIS or GIS, which is a format, but QGIS is a software. This is where the ground truth is created, even though it's very surprising or interesting talking about any ground truth when our target planet is not Earth, because we are not there, and normally ground truth only can be created when you are present. But anyway, QGIS is where the ground truth is created. It is a hand-labeled reference that the model will learn from. And annotators, who are in our case planetary geographists, are working with the predefined classes, for example, crater rim or volcanic dome or ridge, and this annotation is based on shared guidelines. If three people are labeling the same thing in 3 different ways, the model is getting confused. This is why consistency a huge key in our project. With the unified coordinate system, it's actually interesting that I'm talking about a unified coordinate system, because in the case of Venus, there is a Venusian coordinate system, which is not parallel or identical with the earthly coordinate system, which is VGS 84. And when we started to preprocess the image, that we first needed to convert the image to an earthly coordinate system. It was a very key point, because AI models are unable to sense and make consequences when we are not using unified data. The second key point is preprocessing. As I told you, this is a multi-gigabyte radar mosaics, and we need to cut them into smaller types. Usually, they are around 5012 pixels. And the dynamic range is normalized. The second one is training in PyTorch plus SageMaker, because we are going for open source, and everything we are running is running in containers with pinned dependencies and fixed random seeds, and then we evaluate, because we don't stop at simple accuracy. We need to check precision, recall, and we even run dedicated false positive clinics, so to say, where we kind of examining what misled the model. It's like labeling a shadow as a dome, for example. Validation is done across multiple regions to avoid the classic "it only works here" trap. And then we export. The final output comes in GeoJSON and GeoTIFF and immediately usable in QGIS. And here we do the topological cleaning, removing holes, self-intersections, and so on. And then we do the styling. We are using consistent colors and legends, and the whole process is versioned, making it easy to hand over to other teams and scalable to larger data sets. Here I'd like to show you a little about that infamous GIS and QGIS I told about. Anyone here ever used this kind of software? Oh, that's cool. Awesome. Great. Are you using QGIS or using other kind of software? Uh-huh. Okay. Yeah, that's cool. So basically, GeoJSON is a geospatial dialect of JSON. It's almost identical to JSON. It has the same logic. As you can see, we have key value pairs, except the geometry field contains a geographic shape, and the properties field stores metadata. But basically, this is a JSON file. And you can see what is written on the screen. It's not too small. Okay, cool. So basically, this is a minimalist example. And in the type, we have the feature. In the geometry, we have an inner section as a type. In our case, this is a polygon, for example. And then we have properties. In properties, we have class, and crater rim is, for example, a class. And we have a confidence of 3. Which means that we are very confident. I mean, the annotator, actually, not me, because I can't really identify these structures. But the annotator, who is expert in the field, can say that they are sure that it's a crater rim, so the confidence is going to be 3. At first, this looks like a code, but it's actually very, very human-readable data. And it precisely describes what's on the map and how much we can trust it. So the advantage is not only too easy to version, diff, and process with any programming language, but QGIS, on the other hand, is open source. I always say that QGIS is kind of the VS Code for maps. You can open layers, draw polygons by hand, style them, measure them, and export them. And this is where the training examples for the model are born. There's a crucial detail, which I already mentioned before, that the coordinate system must be unified so that all the layers align perfectly. And if there is one big lesson I ever learned from this project, is that your model is only as good as your labels. Because if you label the same phenomenon consistently, that the model will be stable. But this is true for every other project which works from data. When the data is heterogeneous, that the model will be uncertain. And that's why this GeoJSON dash QGIS pair is not just a toolset, but a quality assurance framework as well, in our case. Okay. So this is just a short example of how QGIS works when we try to annotate them annotate a Venus image which is already colored. Our next slide is about the training environment. So when we talk about model training, I always think about it as a controlled laboratory, because we are not only experimenting in our laptop. It runs in a cloud-based, precisely configured environment. Our foundation is AWS SageMaker. I don't know whether you guys are using Azure, Google Cloud, or AWS. I'm very convinced for AWS in the past couple of years, but of course, any open source projects can be founded in any other of these huge companies. But I'm using AWS SageMaker in a managed GPU infrastructure, and they package the code into a Docker container, which is ensuring that the environment is identical everywhere. And to key to the reproducibility, in our case, is the fixed random seed. Have you ever heard about the fixed random seed? Cool. So my easiest explanation for that would be that if it's like planting seeds in a garden twice using the same batch. And the garden won't be exactly the same both times, but it will be very similar. And in our case, this is a fixed random seed. And that's how we make sure that rerunning the training doesn't give completely different results, because then we would be in huge trouble, time and costly trouble as well. And every run is logged. We are using MLflow or DVC with every parameter, metric, or model file and dataset version where it is recorded, so we can never have to rely on memory to figure out why a run worked. It's all well documented. And we also have some practical tricks that we are using in this project. For example, a mixed precision is to calculate faster and use less memory, or we are using batch size tuned to the GPU's memory. And we are very, 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 very careful learning rate scheduling because it determines whether actual training converges smoothly or it's blowing up. And one more principle, which is, I guess, also very important for you too, cost awareness. Because we try to not to launch huge hours-long runs immediately. First, we try small prototypes to see if it's worth scaling up. And this saves both money and time. So in summary, training is not a wild camping. It's a well-equipped laboratory where everything is labeled, documented, and controlled. And that way, the model's results are not by luck, but engineering. The result visualization and making science visible. We always show model results to visualization first, because that gives the fastest feedback. And in case of visualization, we always think in 3 levels. First is the mask overlay on the radar image, and this is the first aha or wow moment when you can literally see where the model codes something on the noisy radar background. As you can see, that first image looks much more human than the other strips, the black and white strips that I showed you. For example, crater rims in red, ridges in blue. It's like using a highlighter in a book. It instantly emphasizes what matters. The second one is the vectorization image, where the colored pixels turns into geometry, polygons, lines, points. And here comes the topological cleaning, and we are always carefully emptying anything so we don't lose any information. And this is the stage where geologists can actually measure. And the third one is the styling and legend. And I try to make it a little faster because we had already 40 minutes and I got 40 minutes. So I'm very sorry about that. Just a couple of more slides for the rest of the time. So a good model by itself is not enough. If it's already runs off the author's laptop, that's not science, that's magic. And the goal for the community is to run it, test it, and build on it. And that's why proper engineering packaging matters. That's why we're using Onyx export. And we save the model in an Onyx format. So you can think of it as a universal adapter. It's run in different frameworks and platforms, be it cloud, edge devices, or another machine learning environments. And then we use Docker, GitHub Actions, and so on. And 2 more slides, which is going to be very interesting. So what is the scientific significance of such projects? First, the crater statistics and age estimation. As I already told you, we have a rule of thumb. The more craters on the surface, the older it is. If we can detect craters automatically and consistently, we can build far more precise age models. And this could shed new light on Venus resurfacing history. The second one is the volcanism. So domes and lava flows reveal the planet's thermal history. And if we map that consistently across large areas, we can better understand when and where activity may have occurred. And how recent it might have been. And also this helps answer the big questions whether Venus is still a geologically living planet today. And the third one is tectonics. And my last slide, before the thank you slide, is Beyond Venus application elsewhere. Because even though we were talking about Venus today, the methodology is much, much broader. The same way of thinking applies to other planets and even here on Earth. So for example, planetary research. The exact same approach can be applied to radar data from other celestial bodies. Think of, for example, future missions to the moon or the Titan. The rule is the same. We are turning radar echoes into some usable map layers. And that means we are building tools that will be useful in the next generation of planetary exploration. The second one is Earth observation. On Earth, radar is kind of a real superpower because it doesn't depend on any daylight or weather. And we are already use it to track, like, I don't know, flood extents, monitor landslide, or measure changes in ice sheet, and even map the spread of volcanic ash clouds in the past. And what we call a speckle-aware pipeline for Venus could directly support real-time disaster management here on Earth. And the third one, of course, is education open science, because a pipeline is fully open and documented. It can run in a university lab as well. Students don't just learn the theory of radar and machine learning, but they can actually try it with real data, which can build the next generation of scientists and makes research more transparent. So this project is not only about Venus, it's about building good geospatial AI everywhere, even on another planet. And thank you very much for your attention. Let me just briefly summarize what this journey was about. So as I told you at the beginning of my presentation, that on Venus, optical cameras are blind, but radar can hear the surface. And from these echoes, we are building our maps. First, raw data becomes a mask, then mask becomes a vector, and then vector becomes scientific knowledge. So every step of this process is done with open source tools like Python, QGIS, PyTorch, SageMaker, and there is no magic in the black box. Everything is reproducible and verifiable. And if you take only one thing home from this talk, let it be that geospatial AI is not about just mapping Venus. It's about a new mindset and a new way to turn raw data into actionable knowledge. And I think that is the real value, basically, and why it's worth engaging in, whether you're a researcher or a developer or simply a tech enthusiast. Thank you very much for your participation.